Okay, now that we have the basics of continuous random variables under our belt, we can begin to apply it and look at a few common uh, random variables that have a continuous distribution. And the first we want to look at is called the uniform distribution. And so we have some interval AB, and we say the random variable x is uniformly distributed on AB if it has a PDF equal to 1 over b minus a on the interval AB. Okay. So notice where the uniform comes from. It's uniform not in the sense of an outfit, but more in the sense of a uniform policy, right? That's a policy that's applied to everyone the same way. Well, notice this PDF is a constant. Okay. Now we can facilitate working with this PDF by introducing this thing called an indicator set function. So if we have some set S, we say that when x is in S, it turns on, it becomes 1, and it's 0 if x is not in S. And so now I can rewrite this like this, where this is the indicator variable where if x is in the interval AB, it becomes 1, and I get the quantity 1 minus b over a for the PDF, and if x is not in the interval AB, it's 0, just like you see here. Okay? And you can show that the CDF, which I get by just integrating from minus infinity to x, right, is equal to the following. If I don't reach a, the CDF is 0. As I'm passing through the interval, the CDF goes up in a linear fashion from 0 to 1. And then when I'm greater than or equal to 1, the CDF stays at 1. Okay? The uniform distribution might seem very boring, but it turns out that actually when we sample on other random variables, it's actually important in the proof of certain sort of sampling schemes, and we'll talk about that a little bit later. Okay, some things that you can show, I'm going to leave this for you to show, that the mean is equal to the midpoint. When you do this integration, okay, you get the average of a plus b, and we would expect that, right? The mean is the center, and for a symmetric distribution we expect it to be at the center of the distribution, so being at the midpoint makes sense. And you can show that the variance is equal to b squared minus a squared over 12. Again, this is something I'm going to leave as an exercise for you. Okay, another distribution we're very much interested in is the exponential distribution. And if x is exponentially distributed with parameter lambda, it has the following PDF. Notice that the range or the support of the PDF is 0 to infinity. Okay, so we can't take on negative values, right? Because this is actually a negative. And let me just for the sake of being really clear, let me put a little space here. Okay, so you can see that very clearly. Okay. Notice that lambda is basically a scale factor. Okay, it kind of takes the place of a half-life in exponential decay. Okay, it's kind of a characteristic length over which the distribution decays. So you notice that if lambda is very, very large, then the distribution decays very slowly. If lambda is small, it decays very quickly. Okay, you can show, and I'll leave this as an exercise for you, that the CDF is equal to 1 minus exponential of minus x over lambda. Again, I'll leave this for you to prove that the mean is lambda and the variance is lambda also. You should be able to derive that from this PDF. So these are the basic properties of the exponential random variable. There's a very important property of exponential distributions, and it's that they are what we call memoryless. It turns out there are two random variables that have this property. If you're a discrete random variable, the geometric distribution has this property. If you are continuous, the exponential does. And here's what it basically says. It takes a little while to get your mind around this. It says, okay, if we let the waiting time for an event to occur have an exponential distribution, and this is like radioactive decay, right? Radioactive decay is basically the waiting time. It has an exponential distribution. Then if you know that the event hasn't happened by a certain time, say t naught, This doesn't give you any information about whether it will occur at t plus t naught. If I write this in terms of conditional probabilities, it says, okay, given that x is greater than t naught, the probability that it's greater than t plus t naught is the same as the probability that x is greater than t. This shows us that they're independent, right? And you can prove this. I'll let you go through the proof, but if we use the probability of conditional, we use the definition of conditional probabilities, we get our first line here. Obviously, these two events are the same as x is greater than t plus t naught. Okay. If I actually evaluate what that is from the CDF, I get the following quantities. This cancels out, and this is just the probability that x is greater than t. Okay. So basically it says that if I know an event hasn't happened up to a certain point, it's as if the distribution is starting all over again. The waiting times from that time that I'm looking at basically now take on a regular exponential distribution. It's an interesting property, and it's very important. Okay, the last one we want to look at is a normal distribution, and I'm sure you're all familiar with the form of the PDF. An important thing to realize is that the support goes from minus infinity to infinity. Okay. The CDF has no closed form expression. You can prove this. And the CDF for normal distribution has a certain symbol. It's capital Phi. Okay. In order to find it, you have to use computational packages. Okay. I'm going to leave it to you as an exercise to show that the mean is mu and the variance is sigma squared. You should be able to do this using what we learned from integration theory. Okay, now there's one distribution that's very important. That's a standard normal, and we saw how to get that already. We made the change of variable z is equal to x minus mu divided by sigma. Okay, and again, there's no closed form expression, but there are tables that we can use to find this. Okay, or we can use a computer package, and of course the mean is 0, the variance is 1. So it's very nice to work with theoretically also. Okay. All right, we're going to move on next and look at two random variables.